Hi everyone, I am Ramesh Adeep. I am a graduate student at University of Toledo from Electrical Engineering and Computer Science Department. Today I will be presenting research titled Reservoir Computing: Empirical Investigation into Sensitivity of Configuring Echo-State Networks for Representative Benchmark Problem Domains. This is the general outline for today's presentation. First, we will cover the research motivation, problem definition, as well as the solution approach. This will be followed by the background for reservoir computing and echo-state networks. I will then give an introduction into the problem domains covered in this research, followed by the empirical study results and findings. Finally, this research will be summarized through the comparison of these benchmark problems to each other and literature. The motivation here is to gain a better understanding of reservoir computing, specifically ESN architecture as well as parameter selection. You may be thinking that reservoir computing is irrelevant when you're considering deep learning because of a lot of things that can be achieved with reservoir computing could be achieved with the deep learning model, such as deep LSTM. However, echo-state network provide us with powerful computational inexpensive models that have surpassed other models in variety of benchmarks including handwriting recognition and financial forecasting. One recent study has also shown that ESN have a weak dependence on size of training set, require less data than feed-forward artificial neural network and LSTM, all the while achieving higher accuracy than both models on the Lawrence 96 chaotic time series problem. Reservoir computer from coding perspective are really easy to implement and understand. Specifically for echo-state network, we will be focusing on there is no gradient descent based training, but we get a network that just as powerful, if not more. However, there is some mystery when it comes to setting up such a model. Setting the parameter or devising the perfect architecture is not something that necessarily can be done out of the box. You have to set the parameter in such a way that the model obtains the echo state property, which is not going to be the same for every data set. Our goal here is to take away some of that mystery and give context to setting up the echo state network through various heuristics and guidelines. This has been accomplished through the empirical investigation of several different benchmarks. Reservoir computer is a type of RNN, but what makes it different than other RNN? The distinction lies between the hidden layer, the reservoir, and the readout layer. Traditional RNN generally use gradient descent based method for calculating of the weight between all the layers. A reservoir computer separates the hidden layer from the readout layer, meaning they are trained completely separate, which greatly simplify the training. Even more simplistic is how their weights are generated for specific reservoir computing, the echo state network. All of the weight within the network, except for the weight for reservoir to the readout layer, are randomly generated. Only the output weight are trained. Even though the reservoir is randomly generated, it acts as a temporal kind of kernel method, transforming the input space to higher dimensional feature space, enhancing separability. Why would you choose an ESN over an RNN? Over the years, new learning rules for RNN have been proposed, but bifurcation, long training times, and dissolving gradient are still evident. Even the algorithms that address these issues are usually harder to optimize and have slow conversion rates. ESN, on the other hand, address a lot of these issues. They do not suffer from vanishing gradient. There are no long training time because of lack backpropagation through gradient descent method. Once you find a reservoir that works well for a set of data, it can be reused with that data for different problems. And it has been repeatedly shown to exceed at handling chaotic time series problems. However, it is obvious that a random reservoir is not optimal. There are new algorithms though which are helping to tackle these issues, including one that uses particle swarm optimization. Now we move on to the results for empirical investigation. For this investigation, we covered 4 different problem domains through 4 different benchmarks. They were time series prediction through NAMA 10, pattern generation through lazy figure 8, chaotic time series prediction through Mickey Glass 17, and time series classification through free spoken digit dataset, also referred to here as isolated digit. Feedback connection have been mentioned as optional in the setup of ESN. However, some problem required. Here the lazy figure 8, which is a pattern generation task required as a goal is to get the ESN to keep generating figure 8 on its own. The Mickey Glass 17 problem was also set up as a feedback problem, but not because it had to be. Having the model continue to generate the chaotic time series problem accurately of its own prediction is just more difficult problem in a general, and having second feedback problem to evaluate was of interest. That being said, NAMA 10 and isolated digit benchmark problem did not need feedback connection. For this experiment, we made several different architectural changes, including swapping out the reservoir activation function, the output activation function, testing various optional connections to the output unit, and testing different weight distribution. The equation in the upper right corner are representative of the various changes that occur for optional readout connection. For any benchmark that do not need feedback, the feedback weight matrix is set to all zeros. Spectral radius, leaking rate, as well as the other hyperparameter optimized for each model. Some trial-specific note. We have already mentioned why lazy figure 8 and Mickey Glass 17 are the only problem to use feedback. Feedback should only be used if it is necessary, like pattern generation, or if your goal is to have a model that produces prediction continuously based on its own output. It generally causes stability issues, so it can cause more harm than good when you use it for a problem that does not need it. A bias was injected as an additional input into the reservoir for all these benchmarks. All the parameters here were optimized using Optuna, and to do so we left n the number of neurons in the reservoir constant, because we could mess with this parameter easily later. Also, rich regression is used to train W out. Another important note is that sometimes hardware constraints cause spike in prediction runtime. So test take make sure that is all it was. These results were double checked on NASA high performance cluster. Metrics used here are mainly RMSE and F1 score, which are fairly common metric for both regression and classification respectively. This figure shows all possible model combinations based on the architectural changes mentioned earlier. There are a total of 48 different models which optimize for each benchmark problem. For NAMA 10, all the models did well, so here only the top 10 are shown. To train the model, the NAMA 10 input was fed to the reservoir for 1200 timestamp, where 200 were washed out. Noise was also injected to help generalize the fit, but not the regularization coefficient could have done that on its own. N was set to 100 during optimization, and after we ran the reservoir for increasing N. One can observe here that for a good set of parameters, increasing N will decrease RMSE. Therefore, increasing the reservoir size N is easy way to improve performance. One of the things observed from the various tests performed on the finalized model was that for all set of parameters, increasing and decrease RMS to some degree, which you can see in the graph on the left. It was also observed for this problem that denser input weight matrix seem to overall assist in prediction capabilities, and one should keep a dense input weight matrix, and optimization is low priority. One can see for the set of graph on the right that denser input weight matrix decreases RMSE. where the value of observed model densities can be seen in the table. The graph on the left shows several models with their finalized parameter set minus the leaking rate value which has been swapped out with the value from other studies. For NAMA 10 there was preference toward value closer to 1 which indicate reliance on the current reservoir state and current input without the need for memory. Several NAMA 10 models from literature do not even use the leaking rate term which coincides with these results. The rightmost graph set look at several models with their finalized parameter set, minus the spectral radius value which has been swapped out with value from other studies. Value closer to 1 decrease RMSE the most and value that straight from that increase the RMSE. This implies a dependence on the history of the input. Various connections to the readout were tested including from the input and reservoir. Just for the reservoir from the input, reservoir with self-recurrent readout connection and just the reservoir with self-recurrent readout connection. A few things are evident from this graph. Number one is the utilizing the extra connection is highly dependent on the parameter selection, meaning the echo state property is important in making use of them. Second, all of the model with self-recurrent condition for the right set of parameter decrease the RMSE much more than those without. It also seems that extra connection from the input to output do not make a difference. The blue and yellow line in these graphs are the model with self-recurrent connection. Let's move on to the lazy figure 8 generation problem. Here 3000 samples are used for testing, that's 15 figure 8 sets, and 20,000 are used for testing, which is 100 figure 8 set. A large washout of 1000 is used here for training and testing, which ensure all the initial transients are removed. The value could have been smaller probably, but the data for problem is easy to generate, so it can be sacrificed. The goal of this problem was to continuously produce the figure 8 pattern and not deviate from that. The only input for this problem is bias value and the value from the output the ESN predicts. If those values have a lot of error, this error is going to propagate throughout the reservoir, leading to an unstable model. To increase the reservoir stability, random uniform noise was injected. The size of reservoir was set to 20 during optimization. In here also, increasing the reservoir size n is an easy way to improve performance for a good set of parameters. Both tangent hyperbolic and sine C make good reservoir activation functions. The identity readout activation is often sufficient given a good set of parameters. This problem functions well for variety spectral radius but most commonly ended up around 0.8, a spectral radius closer to 1.0 correlate to slower reservoir dynamic, implying dependence on the history of the input. Self-recurrent connection in the readout layer improve the performance problem, reliant on previous output or architecture that exclude those connections, but only make different for small reservoir. Injecting the bias term directly into the readout degrade the performance of the model. Setting the leaking rate close to zero indicate heavy reliance on the previous state of the reservoir, which contain information on previous feedback and input. Because we do not have time to go over every single benchmark covered in this study, I am going to briefly highlight the last two. The Mickey glass problem, which was our other feedback-based problem, saw trend towards spectral radius value of 0.8, implying dependence on the history of the input but not so much as NAMA 10 with the lower value. For all these parameters set, it seems like there was dedicated balance between the feedback to input ratio, where in this case bias was the only input. The isolated digit problem had a different setup than the other benchmark because it was classification task where each time series group was independent of the last. This was reflected in the parameter selection with spectral radius value close to zero, indicating reliance on recent input, as well as higher leaking rate value near 0.9 indicate the need for memory, but still most reliant on the current input and reservoir state. There also seemed to be some preference for Laplace and discrete by-value distribution for the weights. It should also be noted that the bias value did nothing for this problem. For all problems, both tangent hyperbolic and sine series reservoir activation were competitive for the right set of parameters. There was a study done that showed that sine C decreased RMSE more than tangent hyperbolic for increasing reservoir size for NAMA 10 Mickey glass, as well as some of other benchmark. But there was not much information on the parameter used, so it is uncertain how much parameter deviated between the model using different activation function. But regardless, that trend was not consistently observed here. Your best bet for testing different reservoir activation may be to just optimize a set of parameters for some chosen function and switch out function after to see if you can achieve improved performance on a model. The right set of graph look at the output activation function. For all these benchmark, tangent hyperbolic and identity readout were competitive in terms of RMSE. So you may as well stick to simpler identity readout. The only problem that the tangent hyperbolic readout activation didn't work for was the lazy figure 8. These graphs look at the influence of uniform, discrete bivalue and Laplace distribution for weight generation. For the most part, they all had comparable performance. Swapping out parameter made some do a little better and other do a little worse, but not by much. I think it is safe to say you can just optimize your model with chosen distribution and then swap it out after see if any improvement can be made. The only problem that may show some preference are Mickey glass and isolated digit. For Mickey glass 17, the discrete by-value distribution does okay. It just seems to be a bit less consistent when swapping out parameter sets. However, the isolated digit problem definitely saw preference for discrete by-value and Laplace. The uniform distribution was not able to compete for any of the parameter set given to the model, but maybe it needs more trial to achieve better parameter set. This can be seen in the bar graph on the right where study 8569 uses the uniform distribution. The self-recurrent connection was the only optional connection that seemed to consistently improve performance in some way for all the regression-based problems. The only problem not assisted by the connection was the isolated digit benchmark, shown in the bar graph where study 346b and study 846b both had recurrent connection and when using the same parameter as model without could not compete. It was also observed that no benchmark benefited from having the input directly connect to the readout layer, specifically if that connection was only the bias. One can observe in the top left graph the peach and dark pink line completely overlap. The only difference between those models is that one has the extra connection from the input to the readout, and it obviously does not help decrease RMSE value. In conclusion, here we investigate 4 different problems in 4 different domains: time series prediction, NAMA 10, pattern generation, lazy figure 8, chaotic time series prediction, Mickey glass 17, and time series classification, isolated digit. A simulation study was performed for all 4 problems to formulate guidelines, heuristic or rule of thumb for echo set network setup. Thank you.